Hi guys, the first sample we're going to look at behaves very differently when run inside a virtual machine compared to physical host. Let's trace it and see what's happening. First, rename the file to exe so we can run it, and start Process Explorer to also monitor any suspicious activity. Run the file, and notice it is blocked in something that looks like an infinite loop and is consuming almost half of the CPU. Actually, it's consuming a full CPU because the virtual machine has 2 cores, as we can see with set affinity. Okay, let's jump into a debugger and see what's happening. Open Immunity Debugger, attach to the process with file attach sample1. Notice here it's paused, attached. Let's allow it to continue. And the program is running. Let's arrange the interface a bit. There. That's lovely. Now, a very interesting feature in Process Explorer is that it allows us to see the whole stack of each thread. So, if we go into our sample, threads, and then stack, notice here the code is executing the instruction as the entry point, main entry point, plus 0x1d38. Okay. If we pause the execution into the debugger, notice here 00401d36, which is exactly the entry point plus 1d36. How do we know that? If we go into the modules by pressing E, we can see that the entry point for the main module is 00400000. Okay. Let's go back. So we have a few ways to bypass this point. Let's first understand what's happening. If we step through the code using F8, we notice that the same small block is being executed. Just a side note here to understand what's happening. Notice here the instruction SMSW that we've seen in the class, which if you read online, you'll find out that it's actually implemented differently inside the virtual machines. So that's why our execution gets stuck here. First option to bypass this is to actually patch the jump instruction, which always leads us back. To patch the instruction, select right click and then assemble and enter nope. That is actually no operation, an instruction that doesn't do anything, and make sure to select fill with nopes and click assemble. Now, if you try F8, notice that the execution continues. So that's one way to do it. Let's exit here and see a different way. We will start the sample again in Immunity Debugger. Okay. Attach to the file, sample1, attach, continue the execution, pause, and notice that what is failing is a test for the AL register, which is compared against 8. So, all we have to do is to modify the AL register by adding 8. Okay. We can see that we have bypassed the test. So simple. Now, what if we want to bypass this all the time without having to use a debugger? We can do this as well. Open Immunity Debugger. Then our sample file. Start the execution. Let's first modify the code as we did before. Select Assemble, enter Nope, Assemble. Notice here the modified code appears with a different color. Further on, we have this interesting option, Copy to Executable. All modifications, copy all. Then we have a new binary, which we will save. Save file. We'll rename it differently, sample1 patched, and save the file. Close the debugger, and let's see if this works. Run the file. Process Explorer. And if we check the threads, notice here there is a different address. So we're not stuck anymore at the same blocking points. And to make sure that the program is actually working, notice here that we have a strange message telling us that this, which is actually a ransomware, has succeeded. Okay guys, so to conclude, in this video we've learned how to trace infinite loops, we've learned how to patch binaries on the fly, and we've also learned how to patch the code for offline execution. Thank you and see you in the next screencast.